This is Fun with Electronics Project 5 Ryan circuit. So the difference between Ryan's circuit and the basic circuit is basically the placement of the 330 ohm resistor that was initially placed at the PNP's collector side and was now moved to the NPN's emitter side. So yeah, so this is Ryan's circuit over here, and basically I'll be using still the Project 4 delay circuit. So as you can see, it says 5 kiloohms and 1 kilohm for the resistors, but the resistor that I'll be using that connects to the base will be 4.7 kiloohms, and for the 1 kilohm resistor that's connected in series with the LED will be uh, 470 ohms instead. So yeah, so I'll fix that and include that um, in the report. So yeah, so apart from that, everything else is the same connection, same inputs, same outputs. And yeah, so that's basically the gist. And here we have the hardware. So as you can see, let me focus. Yeah, there you go. Yeah, so as you can see, the 330 ohm resistor that was connected previously to the NPN to the PNP is now connected here to the NPN. So as you can see, did that for each of the stages, each one, not stages, but for each one. So yeah, so everything else is the same. We have the same 555 timer configuration circuit. We have the same CD4017 circuit, and yeah. So here we have the delay circuits, and yeah. So it was So yeah, nothing has changed really apart from that 330 ohm resistor. So yeah, so let's turn it on. So as you can see, compared to the basic circuit, the LEDs are holding on a bit longer. I think it's due to that resistor that was moved. And this is 1 hertz, since I've tuned the 555 timer to produce 1 hertz frequency that feeds into the input of the counter. So yeah, so now we'll look into the behavior of the circuit when the 555 timer produces 10 hertz. All right, so the 555 timer circuit has been tuned to produce around 10 hertz, and just mind the potentiometer that'll be used for uh, in a minute here. So now it's tuned to produce a clock frequency of 10 hertz. So let's turn the circuit on. And I'm still using 5 volts for the first two circuits and 9 volts for the other two here. So yeah, let's turn it on. All right, see, as you can see, it's barely visible. You can barely keep track of where the light is going back and forth. And this is another demonstration that the placement of that 330 ohm resistor causes an increase of delay in the LEDs, making it a bit more difficult to see the see where it's most brightest, basically keeping track of the movement. So yeah, but you can still see it a little bit. So yeah. All right. So yeah, it's giving the same results, but it's barely noticeable according to the increase of delay in the LEDs. So yeah, so now we'll switch on to the LDR and see its behavior. All right, so now we have RB replaced with an LDR here in the 555 timer circuit. And now let's see what happens. Let's turn the power supply on. All right, so as you can see, it's going a bit faster than last time. And now when I shine the light at the LDR, okay, I believe it goes faster, but I'll have to see the speed of it in dark conditions. So for that, we'll cover the LDR with the finger. All right. After covering the LDR with my finger, I believe it has gone slower. So now when I let go, it goes a bit faster. So let's shine the LDR again. Yeah, okay. It's going a bit more faster. If I shine it away, it's slower. Okay. So basically, it's giving the same result as a previous circuit. Um, and still we're seeing that increase in delay that the LED is producing according to the new configuration. So yeah. All right, yeah. So now we'll move on to the potentiometer, and it should give us the same result as the previous circuit. And yeah, it won't, like, you won't see, I believe you won't see any significant change in the speed, since the range that the potentiometer provides is very little, since its limit, I don't know if you can see, but it says 10K. So basically it's not that much compared to what the LDR gives. And I've mentioned in the previous video, sorry, that the range that this LDR specifically gives is from 240 to 250 ohms to 160 kiloohms, which is a big range compared to the potentiometer. So that's why you're able to see this change in speed in both light and dark conditions. So yeah, so now, but we'll see anyways what the behavior is with with the potentiometer. Yeah. So yeah. All right. All right. So now we have the potentiometer connected in the 555 timer, and just to let you guys know that that RA and the capacitor that are used in the astable mode um, is still being used to create 1 hertz. So basically the values for RA are still 22 kiloohms, and and for the capacitor it's still 10 microfarads for the potentiometer and LDR part. Sorry. So yes. So now we're gonna power the circuit. All right. So now we'll turn the potentiometer clockwise. All right, now let's turn it counterclockwise. Clockwise. Counterclockwise. So as you can see, there is no significant change in speed since, like I said, since the potentiometer offers very little range of resistance compared to the LDR, which its range is quite big. So yeah, so that's why you're not able to see the difference in speed. So yeah, but still, anyways, this circuit works too. But in they're both well, like I mean, they're both like successful in terms of performance, like in terms of functionality. But in terms of visibility, I'll go with the basics since with the delay added, like with the delay increased, you're not able to see where the brightness is going, if it's going back and forth, or if it's going really fast or slow, because there's a since the delay is, gets in the way of that brightness, right? And it's difficult to keep track of the light, basically. So that's why I'm going for the basic idea. Sorry, let me scroll back down. Yeah, so in terms of visibility, the basic circuit takes the win. So yeah, nice.